In this video, I will discuss my strategy for calculating convexity, or the relationship between price and yield for a given bond, as well as why standardizing the bond price is essential for drawing accurate conclusions on a given bond's interest rate sensitivity relative to other bonds. The reason I built this model is because I was reading some Fabozzi. For those of you that aren't familiar, Frank Fabozzi only uses mathematical models to illustrate his points regarding fixed income securities. Although mathematical models can be very useful, since I mainly work in Excel, I figured I would try to translate those mathematical models into an Excel model. The purpose of this model, as I mentioned, is to graph the relationship between required yield and bond price. I selected three kinds of bonds: zero coupon, low coupon at a 2% coupon, and mid coupon at a 7% coupon. To illustrate the relationship, I generated a yield curve that runs from 10 basis points to a little over 4,000 basis points. To calculate the price of a bond at a given required return, I used the following strategy. First, I calculated the net present value of the investment, using the required return as the discount rate. Let's say that our market yield is 5%. You can see that the NPV jumped to $22. However, the price of the bond hasn't changed yet. The price of the bond, assuming that the market is fully efficient, should be the price which sets the NPV equal to 0. So, I GoalSeek the NPV to 0 by changing the price of the bond. Now this means that with a market yield of 5%, the market value of the bond is $61.30. Okay, great. Now I need to expand that same strategy for the 400 or so different yields for each of the three bonds. Obviously, goal seeking roughly 1,200 times isn't an efficient use of time. So I simply built a loop in VBA to run the GoalSeek analysis for me. Jumping into the VBA, there are two main loops here: the B loop, which runs through the three columns for each bond, and the A loop, which runs through each yield. Then I built the C loop to calculate the price at a preset required yield. In this case, that's with a required yield of 10%, which is the median discount rate I used when graphing. That yield will be important when I apply the duration tangent to approximate changes in prices later on. So what does the model look like in action? Let's take a look. When I first built this model, I went ahead and graphed the sensitivity calculations that VBA just generated, the ones that you can see below here. As you can see, the convexity of both the zero coupon and the 7% coupon bond appear to be similar, and appear to actually be fairly linear, similar to a tangent, a duration tangent line. Now we know that a zero coupon bond should have the greatest convexity out of any kind of standard bond. A zero coupon bond divests no cash flows between purchase and maturity, meaning that 100% of its cash flows will be discounted at the final period in the investment horizon, leading to greater interest rate sensitivity. So clearly this visual representation isn't accurate. As an added check, I used the Excel duration formula to calculate the durations of each bond. As you can see, the duration at a 10% yield is the highest for the zero coupon bond. We know that Excel is calculating the right duration because the duration is exactly 10 years, which is correct for a zero coupon bond with a term of 10 years. The issue at hand is that the data isn't standardized dollar by dollar. Because the bonds have different cash flow characteristics, the price of each bond at the same yield will be different for each of the three bonds. For example, for the given yield of 10%, the price of the zero coupon bond is $38.50. The price of the 7% coupon bond is $81.50, and the price of the 2% coupon bond is $50.80. If we were to compare the convexities of the three bonds at yields of 10%, the analysis would be off as the level of investment differs for each bond. So to correctly compare the three convexities, the price of each bond must be standardized. What you can see in this graph is the change in price for an increase in yield, with changes in yield occurring at the bond price of $100 for each bond. Now we can graph duration. You can see that the relationship between convexity and duration being that duration is only accurate as an estimation of price for small changes in yield, holds true. So that's the model I built to generate changes in bond price depending on yield, and my 2 cents on the proper way to graph convexity. Thanks for watching, and I hope you found the video to be informative.